The other limit, where the frequency is large, angular velocity is larger than mu divided by rho b square from the same formulation, leads to a very serious complication. The principle of small cause producing small effects suggests that we may neglect viscous forces if omega is much greater than mu divided by rho b square. This leads to a very strange result, because if we neglect the viscous forces, the only term left in the governing equation is the unsteady term, which is del Vx by del T, and that would become del Vx by del T is equal to 0, because all other terms have been neglected. This is an ordinary differential equation, simply stating that the velocity does not change within the fluid with the time. And if the velocity does not change with the time, how can it accommodate the lower no-slip boundary condition that the velocity of the fluid must be the same as the velocity of the oscillating plate at any given instant? It cannot. So, something breaks down. This suggests that there is something wrong in our formulation. The quantities that we have taken to be the characteristic quantities may not be appropriate for our situation. The resolution of this problem lies in recognizing that the distance Lp through which the disturbance penetrates in time 1 over omega is very small compared to b, the gap. The velocity changes from v sine omega t to 0 over this distance rather than over the whole gap b. This means that the velocity gradient normalized by v naught by b is in error. Only if it is normalized by v naught divided by Lp, the penetration depth, with Lp given as under root nu by omega, would the velocity v star be of order 1. And so, we divide the flow field in two regions. One of thickness Lp under root nu by omega near the plate, and the rest of the region as the second region. The first region is termed as the boundary layer and the second region as the outer region. Viscous stresses can then be neglected in the outer region, as we have shown in the last slide, where we will get v is equal to 0 everywhere as a solution, but they cannot be neglected within the boundary layer, where neither viscous nor steady effects can be neglected. So, the flow solution looks something like this. The unsteady solution is confined to this thin boundary layer of thickness Lp, and a steady solution in the upper part, the outer flow. The main region of the flow, the outer region of the flow, does not even know that there is a lower plate which is oscillating. Before the effect of the oscillating plate penetrates into this region, the direction of the plate changes, and so the effect felt in the outer region is negligible. For the boundary layer region, the unsteady forces are now estimated as mass times acceleration, but the mass now is rho L square delta. Delta is taken to be the thickness of the boundary layer. L is a dimension in this or in the cross direction. So the volume of the element would have 2 dimensions of L and 1 dimension of delta. So the mass can be taken as rho L square delta. And the acceleration would be V divided by Tc. And Tc is like 1 over omega. So that the unsteady forces are estimated as rho L square delta omega V naught. Earlier, it was estimated as rho L cube omega V naught. And the viscous forces are now estimated as mu times the area, which is like L square, and the velocity gradient, which is like V naught by delta instead of V naught by L. So that the estimate for viscous forces is mu L square V naught by delta. Delta is as yet unknown. The ratio of inertial to viscous forces then are the ratio of these two, which gives you omega delta square by nu. Now, within this layer, both the inertial forces as well as viscous forces should be significant. So this should be of order 1. And that gives us an estimate of delta. Within the boundary layer, where viscous effects and inertial effects are to play their parts, the ratio should be of order 1, so that delta should be order of under nu by omega. The same result we got earlier. It is like LP, the penetration depth. This curve shows the variation of delta with the frequency in hertz, and this depth increases as the fluid becomes more viscous. For water, it is less than a millimeter in this frequency range. For glycerine, it is much higher. And this delta increases as frequency comes down. That is when the plate slows down. The vibration of the plate is slower. Then it can penetrate to a greater depth. Let us look at now the viscous flow past bodies and try to apply these concepts that we learned here. The equation that we derived earlier, the Navier-Stokes equation, non-dimensionalized, is this. For flows that do not involve a free surface, we can introduce a non-gravitational pressure. Script P is equal to P plus rho Gz minus P naught. And this simplifies the equation by combining the first two terms on the right. Here we use delta Pc as the characteristic pressure difference. In single phase flow, where cavitation is not involved, delta Pc is not specified by uniquity parameters because there is only one pressure specified. So we can set delta Pc equal to 1/2 rho V naught square arbitrarily. So that the equation now has an inertial term which is of order 1, a pressure terms with a coefficient 1/2 in front of this, and a viscous term. The first coefficient is recognized as the Strual number, and the last coefficient is 1 over Reynolds number. For flows with Reynolds number much less than 1, inertia term can be neglected and the flow is dominated by viscous forces alone. The pressure forces balance these viscous forces and we get an equation minus 1/2 the non-dimensional pressure gradient plus 1 over Re delta star square V star square is equal to 0. This is a linear equation and exhibits very interesting results. We'll study some of them in the next lecture. For flows with Reynolds number much greater than 1, viscous term can be neglected and the flow is dominated by inertial forces alone. The pressure forces balance these inertial forces. The equation is Strual number times delta V star by delta T star plus V star dot delta star V star, this is the inertial term, is equal to minus 1/2 delta star P star. This is a first order equation in velocity and would accommodate only one set of boundary conditions. But on stationary solid boundaries, we have two conditions, that both the normal and tangential velocity must be 0. So obviously this equation cannot satisfy both the boundary conditions. You can see that the problem is developing in the same manner as the problem of the oscillating plate done just now with omega large. There also we could not accommodate both the boundary conditions. Here too we cannot accommodate both the boundary conditions. The inviscid solution of the Euler equation, only the no penetration condition apply and typically would result in a slip at the wall as shown. But this would mean there's something wrong at the wall, because the no slip condition must also be satisfied at the wall. And this can happen only if the velocity is changing too fast, too quickly in a very thin region near the wall, such that the velocity gradients are large. And so, for the velocity gradient, we cannot take the dimension of the body to be the characteristic length, but the distance over which the velocity changes from 0 to the inviscid value should be taken as the characteristic length in the normal direction. We introduce a non-dimensional distance variable, eta is equal to x divided by delta. And this blows up the boundary layer within which these shear stresses are not negligible. So we consider a layer of thickness delta. This is the inviscid profile. The viscosity produces a sharp pressure gradient within the boundary layer, and we get a solution that looks like this. The two solutions, the outer region solution and the boundary layer solution gives rise to a velocity profile that looks like this. The velocity rises very sharply from zero velocity to a maximum velocity some distance away from the wall. And then in this outer region, viscosity is neglected and we get a solution which is inviscid. So this part represents the inviscid solution. The two solutions merge together at the edge of the boundary layer. In fact, the boundary condition needed to solve the boundary flow says that the velocity at the edge of the boundary layer should be equal to the velocity at the wall given by the inviscid flow. This is a very interesting problem and we will spend considerable time to this problem of boundary layer flow. The boundary layers on blob bodies play a central role in the dynamics of fluid at large, Reynolds number, and we shall explore it in some details later. Thank you very much.